let's start with considering where are we, other than in Corvallis and, you know, sitting in this room and so on. I proposed at the beginning that we try to explain onion skin weathering, and that I just want to remind you that, you know, that's a thing, and that we would like to try to explain it. We haven't done so yet, I don't think. But we have considered several mechanisms for breaking rock so far. So let's just briefly review those. We've talked about spallation, wherein the strain of expansion at the outside of a rock relative to the inside of the rock causes enough stress for some rock to pop off the outside. So, you know, theoretically that could do something like that, I suppose. Frost cracking, in which we've got heave pressures due to ice crystal growth in cores. Root damage, in which we've got, say, wind moving the roots, and the roots wedged into the rock and therefore moving the rock, breaking the rock. And so we might simply ask at this point, should we consider any of these mechanisms viable for producing something like that? Spallation maybe, but remember that the mechanism needs to work in a particular sort of, well, mechanism. Okay, so spallation happens when you've got a fire. And I showed you pictures of like bits of rock off of a boulder. That's a stream bed. So it's unlikely that that's going to cause rock to break in a stream bed. We've also got to, it's got to be able to happen under like 4 meters of soil and weathered rock. It needs to happen in wet tropics and temperate climates as well. Yeah?
Just looking at rocks that fully good heat compression, would that also kind of line or some type of layering?
So there is this idea of, what do we call it? Not unburdening, but unloading, in which, say, if I've got confining pressure holding rock together and then I remove that confining pressure, can I simply pop off sheets of rock?
Or at least not get started.
And I'm not real clear on that. One of the things I haven't really talked about, though, is sort of, in general, the sorts of stresses that might pop off rock due to simply gravity or tectonic structural pressures. And I could just briefly talk about what is going on there. So if I've got, say, a cliff, something like that, and I've got all this overburden of rock, and I've got some convexity here, then let me draw it a different way. Draw it like this. If I, in general, have stresses, pressures that are tangential to the surface of the rock, then at some point of high curvature, the resultant of those surface tangential vectors will be outward normal. And that is thought to at least help along the cracking of rock in a lot of cases. And in particular, if I had some overburden here and then I removed that overburden, then, you know, again, that would help for that kind of pressure to result in rock breaking. And this is the sort of mechanism that people have called on in particular to explain sort of retrogressive failures up bluff faces, sort of the creation of sort of undercutting parts of cliffs, you know, where the that overburden of rock tends to result in it popping a bit. I'm not sure how much. I'm not sure whether I buy that. I mean, it seems reasonable. There are some pretty extreme cases. They're like YouTube videos that you can find where some guy is standing around and he sort of hears some weird noises and happens to point his video at this rock face, and all of a sudden the rock on the rock face just all pops off, like literally up into the air kind of thing. Is that due to some kind of tectonic motion nearby that's increased local stresses? I don't know. I've seen those videos and I don't actually know if anybody's explained in particular what happened at that particular sort of case. But that's a thing. And it...
I think someone said it before.
Is that what you're pointing at? Would you like to come in? Okay. If you have your quiz, I'll take that. Please. So, I don't know. I guess while that kind of thing, this sort of massive popping of rock on a video, obviously there's a thing going on there. I do kind of wonder in general if people are sort of reaching on this kind of, I don't know. So, I think that it's definitely worth keeping in mind, because I think it can be important, especially when, in that case of cliffs. But I think you probably also need other things to get the cracks going. There is an element, in reading some of those papers, sometimes they'll simply say, a rock is really just weak. We really don't need to explain how those cracks get started on some level. Because if there is any tension, eventually it'll break. Well, okay, but really, I mean, I don't know. So yeah, that's the thing. I think, it also kind of suffers from, in terms of explaining something like rhinelet formation, that kind of thing still, well, again, let's consider what we need to happen. We need for this to be able to happen under meters of material. We need for it to happen in a variety of climates, but in general, wet climates, maybe dry climates as well, tropics to temperate climates, maybe in sort of periglacial climates, the frost cracking trumps this stuff. Yeah, Ethan?
Is it all chemical, just like the degrades parts of the rock into a outer shell and then just keeps doing that over and over again until it...
Well, it very well could be. So one of the things that we haven't, the mechanism that I did originally list under physical weathering processes that I haven't gone into in any detail is salt cracking. And now that I've turned off those lights, I realize that I have some great pictures of the results of salt cracking to show you. So salt cracking is when you grow salt crystals in rock. And so according to the book, and I just write this, pardon the flipping on and off of the lights, hope you won't, if it doesn't make you queasy or anything. So let's consider salt cracking, at least briefly. It's analogous, supposedly, to frost cracking. So that is, we've got that salt crystals grow in microcracks. The pressure of crystallization leads to stress. And it's in particular important in arid environments and intertidal environments. And it seems to lead to some pretty interesting disintegration in general of rock. Here's a case in southern Utah, the Paria River, and we can see that between low and high water, perhaps, we've got these formations called that are called the windows, and that's a person there for scale. So these are the person-sized, person scale holes in the rock, presumably created when the river rises, deposits salts in there, the river goes back down, it's dry, so the water evaporates, leaving behind the salt crystallizes, forming salt in there, and the rock kind of disintegrates. You see some really cool features in the intertidal. This is happens to be in British Columbia. The seawater will tend to gather in these holes once they get started, and then, as the tide goes back out, once the tide goes back out and the water evaporates, again, you start getting salt crystals forming and disintegrating the rock. Now, none of this particularly looks anything like onion skin weather. But I don't want to rule a mechanism, or at least something like that mechanism, out just yet. Rather, I think these are examples of precipitation of dissolved salt, like salt, NaCl, as water evaporates.
How does the growth of salt crystals on that create holes into the rock? I feel like in my mind it would just grow up.
It's not the crystals growing on the outside of the rock, it's the crystals growing on the inside of the rock.
Oh, okay. So it's not like...
So it's the water seeping in, the salt water seeping into the rock, and then as the water evaporates, leaving behind the solid. Yeah.
So how is this different from, say, zeolite formations or quartz filling in with their secondary mineralization? How is it different from salt cracking? Why do you see these phenomenon of salt cracking rather than you just see veins filled with quartz?
Gosh. I'm so ignorant of those things that I'm not sure I want to even speculate how they might be similar or different.
The difference in supply, right?
What's that?
The difference of what type of neurological supply you get from here, that was just fun to say.
I mean, I don't know if what we're talking about is fundamentally different. Anytime you have a precipitate, we want to think about, okay, what puts the stuff in solution, what gets it to the spot, and what makes it precipitate. And so, yeah.
So, could it have something to do with maybe that these salts are dissolvable in water, not to get removed in that? Because the quartz veins don't want to get removed, right?
Right, it can't be very really hard to water the quartz vein, but calcite vein is also formed in some cases, quartz been formed, and they all stay there, but they can also be watered too.
Those
But
will have hot, liquid, hot hydrothermals compared to the salt.
Yeah, I think it's just locationally and less what's supplying you. If you're, by the ocean, you're gonna have any scale precipitating versus
So
I feel like it's all
a lot of you just.
you guys are
rock
very
like
quickly
also.
getting way over my head. The geology and stuff, hard rock stuff is not my thing. But what I do think we ought to think about then, well, I want to talk about chemical weather, because I want to talk about how do we get solutes in solution in the first place? And how might we get solutes in the sorts of places that might potentially do stuff like that? So that said, I want to just talk about our basic chemistry of weathering. I mean, it's not anywhere near as complicated as some of the stuff that you guys are talking about, so shouldn't be hard. If you guys understand that stuff, I think this stuff will be easy. When we're talking about, sorry, I'll get it. Blank. Here we go. Blank. Okay. So let's talk about solution. When we talk about solution, we generally break it up into two varieties: congruent and incongruent. Congruent, incongruent. Yeah.
Is this chemical weathering that we're going to?
We are talking about chemical weathering, yes. So let me make a bigger heading. Point. We're talking about chemical weathering because, I mean, even though I want to know what physically breaks rocks into those ringlets, if it might have something to do with precipitating minerals, then we need to know how those precipitates get in the solution in the first place. And then we got to try to figure out, okay, how might, well, what does solubility depend on, and how might solubility change such that we get precipitates in such a way that could produce this sort of onion skin weathering, if that's, I mean, we're kind of running out of mechanisms at this point. Frost cracking, isn't, I mean, even if frost cracking could produce these nice uniform ringlets, it's not going to happen under 4 meters in a temperate climate, much less a tropical one. Even if spallation, due to fire, could produce these nice uniform ringlets, again, it doesn't happen underground. What was the other one that we had as a candidate? Root damage. Yeah, I mean, roots probably need some cracks to get going in the first place. We saw in the case of the brick sidewalk, the roots follow the cracks that already exist. So it doesn't seem like necessarily a good way to produce lots of concentric ringlets. Yeah.
These ringlets, do they happen in like a certain type of rock typically, or can they happen in like any rock?
That's a really good question. I think there probably is some limitation to the types of rocks that they occur in, but they do happen in a lot of different rocks. You can see them because the picture I was just showing you was a sandstone, but you also see it in lots of igneous rocks. So, yeah, but we ought to think about, well, just because one's an igneous rock and the other's a sedimentary rock doesn't mean the chemistry. I mean, that sedimentary rock may just be little ground up pieces of that igneous rock without a whole lot of chemical alteration. So if that's the case, then all we need to really consider is, okay, well, what's the chemistry, and then how can the water move through and do the dissolution that it does. Does that make sense? So for chemical weathering, in general, we're talking about dissolution, and we typically divide that up into congruent and incongruent. The congruent is when we simply dissolve the solid and the solid composition is left unchanged. So let me write that. And there aren't all that many minerals that go through congruent. I don't know whether to say congruent or congruent. Congruent's what I learned in geometry class, so I'll go with that. So congruent dissolution happens in a relatively small number of minerals. Halite, which is just NaCl, gypsum, which I'll write up for picks. Let's write up gypsum. That's just calcium sulfate in hydrous crystals, typically dissolving into calcium ions and sulfate ions in the water. Of course, quartz does dissolve congruently, not as quickly as gypsum or halite, of course, but we simply have SiO2 in solid phase. Let me try to get into the habit of noting where things are solid phase and where they're aqueous if there's any doubt. If I've got just ions, then we know those are in aqueous phase. So here we just have quartz and water, and we get silicic acid in aqueous form. And now one of the more interesting, perhaps the most interesting congruent dissolution reaction is carbonate dissolution. And it's interesting for a number of reasons. It's interesting because it makes karst, makes caves and conduits and so on. And it also has a sort of interesting temperature dependence. So let's look at calcite, which is just calcium carbonate. We need to divide it into solid reactions and gas reactions in order to understand what's going on here. So I'll write the solid one first. That's just calcium carbonate, CaCO3 in solid phase, plus carbonic acid in solution, and giving us calcium ions and bicarbonate. The gas reaction is where we've got water and we've got CO2 in gas phase, and that the dissolution of the CO2, the carbon dioxide, in the water gives us the H2CO3, the carbonic acid, in aqueous phase. So, what do we know about chemistry in general? And I'll talk about, we'll get to like equilibrium constants and that kind of thing. But in general, say I'm at equilibrium and I add more reactants, then I'm going to push that reaction to the right. Right? So anything, so the gas reaction here is pretty important because it's something that produces more carbonic acid. And so anything that produces more carbonic acid is going to drive carbonate dissolution. And the reason this is where this gets interesting is because the importance of this gas reaction to the solid reaction makes for an interesting kind of paradox relative to what we're used to in terms of chemical kinetics and reaction rates and so on. Okay, what do I mean? Well, in general, solid reactions, dissolution, solid dissolution is favored with higher temperatures. That is, the higher the temperature, the more soluble something's going to be, the more quickly it's going to dissolve as well. However, with gas, it goes the other way around. With gas is more soluble when temperatures are lower. So in this case, for carbonate dissolution, the enhanced solubility of gas at colder temperatures and therefore the increased concentration of carbonic acid trumps temperature. And we actually get a dissolution, so-called simple dissolution reaction that is actually favored at lower temperatures. So, like in where I'm from, in the Ozarks, in the summer the water is clear, and in the winter the water is this milky green. And why is it milky? Well, it's milky looking really because of colloids in there. But how did the colloids get in there, and why are they in such higher concentration in the winter than in the summer? Well, it's because the clay is in the limestone, and there's a lot of limestone in that area, and in the winter the limestone dissolves more quickly and more of it, and so you get also more of the dissolved shale, clay minerals, or the colloidal clay minerals that come along for the ride with the dissolution of the carbonate. Hence the milky green water in the winter. And if I've been thinking, I have some beautiful pictures of that milky green water, but I didn't put any in my slide presentation today. Sorry about that. I'll have to do that for next time. So this is interesting, I think, and so it means that Arctic rivers have some of the greatest chemical denudation rates because they'll have such high carbonate concentration, or they'll have such high concentrations of calcium and bicarbonate due to the carbonate dissolution. All right. Let's contrast that then with incongruent dissolution. And that is when, incongruent dissolution is when the solid composition is changed. That is, we get secondary minerals. So, in particular, when we've got aluminosilicates, so feldspars, other aluminosilicates, that's how that stuff is going to weather. So the general, let me let's see. Yeah, let me just write up our general incongruent is we've got some aluminosilicates in solid phase. We add, say, water And in this case, I'll just write it as carbonic acid, although we could use other acids as well. And on the other side, then we get clay minerals, again in solid phase. We get cations, that is positively charged ions in aqueous phase. In the case of carbonic acid, we also get bicarbonate and silicic acid. We could have other acids, organic acids, that are the result of decaying organic matter can be involved. Sulfuric acid, nitric acid. In general, carbonic is the most important, although in a few minutes we'll talk about oxidation, and got a lot of pyrite, you can create a lot of sulfuric acid. All right, let's just look at picture 2. Well, first of all, this is not an example of incongruent dissolution. This is probably simply congruent dissolution of amorphous silica, amorphous quartz. These are pieces of chert that we gathered in Arkansas, and Jack Zonka, my former recent PhD student, sawed them in half and put them on scanners to look at the weathering rinds and measure the thicknesses of those rinds as a measure of relative weathering and trying to get at cliff erosion rates. You know, if the cliffs are eroding more quickly, then you get thinner weathering rinds. These two pieces of chert, the black and the white, come out of the same formation. It's a Mississippian limestone formation called the Boone Formation in northwest Arkansas. In this one, you can particularly see what's going on, and what he measured was simply where you had porosity change and where you didn't have porosity change in the rock. So at the outside of the rock, it's dissolving away, and holes are forming in the rock and leaving behind this sort of spongy looking exterior. So that's just quartz weathering. Let's see, is that showing up all right? This is a calcium plagioclase to kaolinite reaction. So calcium plagioclase here plus carbonic acid plus some oxygen gives us kaolinite, calcium ions, and carbonate ions. In particular, I've put it up partly in this form because it shows us that we do get the potential to precipitate calcium carbonate if we suddenly lowered our solubility or something, or increased our concentration. And here we go from this is pictures of unweathered granite versus weathered granite, in which you've got kaolinite mucking up the exterior beauty of that particular granite. No longer shiny as in the left-hand slide. Okay. Now there are different ways to write these reactions, so it gets a little bit confusing. You might see this written in lots of different ways, but the basic issue is that you are taking out these mobile ions, in this case calcium, and you're leaving behind the hydrogen ions from the acid and producing the secondary mineral. You're changing the chemical concentration, you're changing the chemical composition of the mineral and therefore making a new mineral. And so in addition to stripping out calcium ions, these sorts of reactions will strip out the other mobile ions like sodium and potassium. So we also could have potassium or sodium plagioclase, which would give us sodium ions, and so on. Now, so that takes out our mobile ions and leaves behind in relative abundance then the immobile stuff like aluminum and iron. And in particular, those ions of iron that are particularly insoluble, which brings us to oxidation. But before I zoom ahead to oxidation, is this reasonably clear? I mean, if you guys are understanding the chemistry of like all these that you were describing, it's that I don't understand, then I think you're probably good with this. Again, all you need is acid to give up the protons and take away the mobile ions like calcium and to some extent magnesium with potassium, sodium, and so on. All right. Let us then move on, segue as it were, to oxidation. Let me just leave us with, okay, if we're potentially precipitating salts as a mechanism for chemical or physical weathering, then this is one way to get those ions in solution, as calcium ions and say carbonate ions, if calcite is the thing that we're precipitating. Otherwise she gets locked out and then I have to go all the way back over there. Let's talk about oxidation. But let's also remember that we can have the counter to oxidation, which is reduction. So the most important oxidation reactions are generally going to be ferrous to ferric iron and sulfide to sulfate. So the great example then is pyrite, and we do that in 3 steps. So 1, we dissolve pyrite and oxidize sulfide. So that looks like FeS2 in solid phase, 7 halves O2 plus water gives us Fe2 2 plus. This is soluble ferrous ion, soluble ferrous iron ion. We got sulfate and some leftover protons. Stop crowding here and get the second step over here. So our second step is to oxidize the iron. So we take that nice soluble ferrous iron, we combine it with some O2 in solution and give up the proton, and we get ferric iron and water. So again, this is insoluble ferric iron. This is what stains your the toilet bowls in the building orange over the weekend, because there's hella dissolved iron in the water in this building, and then it sits there in the toilet bowl and oxidizes and precipitates out. Because that's then our third step, is because all this was aqueous, but once we go to ferric iron is particularly insoluble, so we're likely just instant presto changeo going to have to precipitate that stuff out. So we got ferric iron plus some water gives us this ferrihydrite and some more protons. So let's write the sum of those reactions, because that's kind of interesting too. So again, we've got the pyrite, solid form, we add a bunch of oxygen, some water, and we get our ferrihydrite. We get some sulfate, and we get some protons. What's that? Well, another way to write that would be sulfuric acid. This is what makes acid mine drainage. So if you go into a place where there's lots of naturally occurring pyrite and you break a lot of rock and thereby give water access to all that soluble pyrite, you can get really, really wicked acidic drainage from that. So I think there are some places in California where the streams are running with a negative pH, like that's a thing. What does that mean? Negative pH means that the hydrogen ions are more than, just the pH scale isn't really working too well for you at that point. But yeah, so you can produce lots of sulfuric acid, and then of course sulfuric acid will help along all sorts of other weathering, including aluminosilicates and so on. Dissolve away enough of that, maybe you expose more pyrite, so on. Yeah?
Those two sulfuric acids, are they in combination to the side of the equation? Is it just,
I'm just sort of,
okay.
you know, that bit there is, you know, we could also write that as aqueous sulfuric acid. You know, we wrote it looking all innocent there, you know, put the couple of sulfate ions first and then some protons and go, huh, those protons mean acid, don't they? No, sulfuric acid. Now, let's just look at some pictures of stuff that's oxidized, not pyrite, but because you know that oxidation of iron is pretty common reaction. Here's some a rock and another rock from my personal collection. You know, the sort of geek I am is that, like, you know, I pick up particularly crusty looking rocks sometimes, as long as they're broken and you can see the weathering lines in cross section. And that's pretty sure these are just basalts unless there's something slightly more complicated than that. But these are both, this one is just from McDonald Forest up on Dipple Hill, and this one is from the coast, like Seal Rock area. Now, the interesting thing about oxidation, though, we think of it as a one-way ticket, but it's not. This is my canoe, and these are, in the background is a gravel bar on the John Day River near Mitchell, and here are a couple of pieces of mafic rock, probably basalt, that I literally pulled out of the cliff on the other side of the river. Because I was curious about this rock, because while all of the other exposed basalt all over the landscape is orange, or, you know, crusty, rusty looking, the stuff sort of between summer low water and winter, you know, sort of base level stand is shiny black. And so I was interested to see whether the water, being underwater for a lot of the winter, was inhibiting the oxidation of the rock, or whether it was reversing the oxidation of the rock. And so what we see is that the interior of the rock is oxidized, and the exterior has a sort of reverse grind on it of reduction. And yes, it turns out there are microbes that do this, that use iron, and specifically they use it as an electron receptor. So they reduce the iron in this odd looking inverse grind kind of way, which I thought was particularly cool.
So are they
Getting this sort of
leaching?
decay. Yes.
Are they leaching the iron out of the rock?
Oh, that's a good question. I don't think so, though. Because I think it can go back and forth. In fact, I've seen it go back and forth, or at least so there was a stream that I did a lot of work in the Coast Range, sandstone, chocolatey brown in the summer, went back in the winter, and it's like this bluish gray. And initially I thought, oh, that we've had some rapid bedrock erosion, and then I saw moss growing on it. It's like, okay, no, it just got reduced. And then next summer it probably went back to being chocolatey brown. So, yeah, I don't know whether the oxidation part is also microbially mitigated or not. I don't know. Because, anyway. Well, looks like we're about out of time. So we'll have to wait till next time to talk about, okay, first of all, how do we talk about the propensity for reactions? We need to talk about things like equilibrium constant, solubility products, saturation index, that stuff. And then we also need to, in order to analyze, say, the weatheredness and weathering in general, we need a measure of the loss or gain of elements, and so we need to do mass balance on the mobile and mobile elements in the rock in order to make sense of the graphs that people make of exactly that thing to show us what's happening in those weathered exteriors of the rock. And hopefully, then that will get us, if we learn those things and we look at the data, that'll help us, I think, understand onion skin weathering.
We're going to talk about that today, right?
Yeah.
Does science know why onion skin weathering happens?
Like 5 people.
Like 5 people.
Well, plus whoever I taught it last year. So that's my opinion.